Alright, welcome back. We're on to our third video in matrices, and we're going to start just reminding ourselves about something called the identity matrix. Now, you might remember that we introduced it earlier, and the identity matrix basically contains only ones and zeros, and the ones are on the main diagonal. So we can see here we have a 2 by 2 matrix, and this identity matrix has our ones here and here, and the rest are zeros. So let's have a look. The identity matrix, okay, we label it as capital I. It's also called the unit matrix because it's just like with our normal numbers, we have the unit 1, okay, which when we multiply anything by 1, the number being multiplied by that remains the same. Well, it's the same with matrices when we multiply by the identity matrix or the unit matrix. Okay, when a matrix is multiplied by the identity matrix, the original matrix does not change. Okay, so if we have our matrix A here, which is a 2 by 3, and we multiply by our 2 by 2 identity matrix in this way, okay, I times A, so we've got our identity matrix first, because remember the number of columns in the second must equal the number of rows in the first matrix. Okay, so we've got I times A, and so when we follow that through, okay, I won't go through it, but you can check it. Okay, 1 times 2 plus 0 times negative 1 will give us 2. Alright, 0 times 2 plus 1 times negative 1 gives negative 1, and so on through the remainder, so it remains unchanged. So I times A is A, effectively. Okay, and it's just got a little note here that A times I isn't possible because the number of rows and columns. So just remind yourself of that, go back over and check why that's the case. Okay, just those fundamental understandings are really important. Okay, but the note here, if A is a square matrix, then we'll find that it is doable, and that A times I would equal I times A to give A. Now, let's move on. The determinant and inverse of a matrix. Say we have a matrix A, which is a 2 by 2 matrix, and we're just labelling it as A, B, C, D for the elements within it. The determinant, okay, is a scalar quantity, so it's like a little calculation we perform on the matrix to obtain a particular number. Okay, that's why we're calling it a scalar quantity, and it's found by using the following formula. Okay, so we often have the determinant of A being represented by det, det A in brackets, and we work that out by going A times D, which is our main diagonal elements multiplying together, A times D, minus B times C, that's our reverse diagonal. So first element here multiplied by the fourth one, minus the second element times the third, so A times D minus B times C. So if you always remember to label your matrices, your elements within the matrix in this way, and think of it as A, B, C, D, then remembering this formula is nice and easy. A times D minus B times C. Another way we can write the determinant is simply to put these vertical lines either side instead of these brackets. By the way, we don't have to have square brackets. Oftentimes we use like large parentheses. Okay, so we might have A, B, C, D, like that. Okay, that's equivalent to having the square brackets. They mean the same. But if we have just straight lines, then that's what we mean by that is the determinant of A, if A is that matrix. Okay. Now it should be noted that these vertical lines in this case are merely a notation. Okay, they do not mean absolute value. Okay, so the determinant can be negative. Okay. Alright, so let's have a look at a particular example. And here we have matrix A, which is 5, -2, 3, and 1. Now our determinant, remember, is our main diagonal elements multiplied together, and we subtract the reverse diagonal elements. Okay, so we've got 5 times 1 is 5, and -2 times 3 is -6. Okay, so subtracting the one from the other, we end up with 5 minus -6, or 5 plus 6, which is 11. So the determinant of a matrix is important, okay, because it allows us to determine the inverse of that same matrix. And we use the inverse when we're looking at effectively division of matrices. Okay, so that's where it sort of comes in. We need it in terms of determining the inverse. So when because when any square matrix is multiplied by its inverse, the identity I is obtained. Alright, so the inverse of a matrix A we write as A with a superscript -1. So it doesn't mean to the power of -1 necessarily, it's a notation. Okay, the inverse. So A times the inverse of A gives us the same result as the inverse of A times A. So the order here doesn't matter in terms of multiplying the inverse with its original matrix. When we multiply them together, whatever order, we get our identity matrix I. Now, so if A is a 2 by 2 matrix, then basically what we get is when we multiply them together, we get our 2 by 2 identity matrix 1, 0, 0, 1. And this is how we find our inverse. The inverse of A is found by going 1 divided by the determinant of A and multiplying that by, remember that is a scalar quantity, multiplying that by, now notice the change here, A and D are reversed positions and B and C have opposite signs to what they originally did. Okay, so let's just note it down here. We've got normally A, B, C, D. Okay, so that's what A is. In order to find the inverse of A, it's 1 over the determinant of A, and we multiply that by the matrix. Now A goes to D and D goes to A. It's D, A down the bottom there, and B and C simply have their signs reversed, but their positions remain the same. Okay. Alright, this is not the only method, but for our purpose in this course it is the most convenient, and it's easily done on the CAS calculator. Alright, now in this course we're only really dealing with 2 by 2 matrices, which is nice and easy. If you go on to university and do first year mathematics at university, they become a little bit uglier. Okay, your determinants there are a whole lot more complicated when you start to get into 3, 4, 5 by 5 and so on. They become messy. Okay, now let's look at a particular example. We've got our matrix from before, A being 5, -2, 3 and 1. The determinant of that we worked out before as being 11. 5 times 1 minus -2 times 3. So our inverse, we go 1 over our determinant. So that's 1 over 11. And you'll notice here 5 and 1 are reversed positions. So now we have 1 here and 5 down there. And our signs for our second and third elements, -2 becomes +2 and 3 becomes -3. Okay, and so then what we do is we multiply our scalar quantity at the front, which is 1 over 11, by every element within the matrix. So 1 times 1 over 11 becomes 1 over 11. And the next one we have 2 over 11, and then negative 3 over 11, and then 5 over 11. Okay, so that's our inverse. So if we were then to multiply this by our original matrix, we would end up with our identity matrix. So we'll leave it at that for this video, but before you go on to do any more questions, okay, we'll just we'll do the next short video, and then you can go on with some further problems. Okay.